Alright, so today I'm going to show you how to automatically project any data set to an appropriate UTM zone using ArcGIS. So at my work, I'll often get data that comes in some kind of global coordinate system, usually just WGS 84 unprojected or EPSG 4326 for those of you who go by codes. And if I need to do some sort of analysis with the data, I need it in linear units like meters. What complicates this is I get a lot of data from all over the world, so I don't always know off the top of my head what the best projection is. And so I'm going to show you how I work through this. And so more specifically in this video, we're going to use ArcPy to create a geoprocessing tool to do it. So this video will be first more Windows oriented, since ArcGIS doesn't run on Linux, and second, it'll be more focused on Python and really using object-oriented principles to write your tools. So if you're sort of familiar with Python or trying to start learning ArcPy, I hope this will be a helpful example for you. And just a quick word before I move on. I like and use both open and proprietary GIS. I don't have an ideological stance on it. I'm a practical guy. I just use pretty much whatever makes the most sense at the time. But that said, there are two things that I like about ArcPy that I want to mention. The first is that it is delivered as a Python package or meta package, and you work with it in idiomatic ways. So what I mean by that is it's not like, say, PyQGIS, where it's delivered basically as a set of wrappers around the QGIS C++ API. So if you're fluent in Python already, ArcPy will not be mysterious to you. And yes, there are pluses to PyQGIS in that much more of the base QGIS functionality is exposed, and you can write really full and rich plugins in pure Python in PyQGIS, but it's honestly a huge hassle to work with if you don't need to use it every day. It's very challenging to find support. The documentation rather is for the most part pretty lean, and that's the second thing I like about ArcPy. The documentation is just phenomenal. Here's an example of a documentation page just for a real simple create feature class function, and these kinds of pages exist for pretty much every function inside of ArcPy. It'll give you an explanation about exactly what it does. It'll give you some usage. It gives you both parameter explanations for the in-app tool, how to use it if you were actually invoking it from within the actual GUI, or if you wanted to script it up. It gives you full Python explanation of the parameters. And then it will also have at the bottom both samples for using it interactively with the console, with the Python console in ArcPro, and it'll give you an example of how to use it in a standalone script. So it's just really fantastic, and virtually everything is explained, and that's just what happens, I guess, when you pay a whole bunch of people to actually do this. I mean, you get this. Many people think ArcPro is basically way too expensive or out of their reach. For those of you, at least in the US, you can sign up for the ArcGIS home use license. It's like $100 a year. I mean, $100 a year for probably what would be almost $10,000 worth of software if you bought it retail or for an enterprise. And I'm not shilling for Esri or anything like that. I just think that's a crazy good deal, and it opens up the technology to a lot more people. And I'll leave links for all that stuff below. All right, so let's get to it. So this is how I dealt with the problem of unprojected data coming in, and I might not necessarily know where the right zone is to project this to. So I wrote a tool that just uses UTM as pretty much a good compromise, and it automatically projects whatever content you've got loaded, or really any kind of vector or raster content, to an appropriate zone. Now the principle is very simple, and what I'll do is I'll walk you through the Python itself at this point. So we've got the doc string, we do our import calls. It's very, very simple. It just imports ArcPy, the OS module, and the system module. Now what I'm doing here with this UTM grid variable is I'm storing basically the entire UTM zone grid for the whole world in this in a string, and keeping it in the or actually rather in a dictionary, and keeping it in the script itself. If you were going to use this in production, you could take this and stick it in a sidecar JSON file or something like that. This is just for demonstration purposes. So we have the GeoJSON grid of the entire world, all the UTM zones in the world. And that also kind of is helpful for because it'll give you the accurate geometry for places around for the zones around like Scandinavia and stuff that are not exactly square, and where you can't necessarily just go by lines of longitude. So just walking through the tool and how it actually works, a lot of this is already explained in the ArcPy documentation, so I'm not going to go really deep into it. You basically have to express a class called Toolbox, and this is pretty much standard. You just fill it out with your label, your alias, your tools. Those are basically your class properties for a typical toolbox, and then you build a class with your actual tool. And so I've called this Utimizer because it basically converts things to UTM. So you call just when you're using the ArcPy package, or that's your interpreter, and you call the object that will automatically prep your tool with a number of maybe the better way to say it is that when you actually issue these specific method calls, the toolbox class will know how to interpret it. So as with all classes, we start out with an init file, or with an init method, just the constructor. We give it a name, we give it a label, a description. All these are pretty much just plain text. And can run in background is just a standard flag for any geoprocessing tool that you create in ArcGIS. The first, there are 1, 2, 3, 4, 5 standard method calls or actually 6 standard method calls in an ArcGIS Python Toolbox. We've got get parameter info, and that's where we actually set up our parameter. This is what the user is going to see when they actually want to go and interact with the tool set. So we just call the parameter class, and then basically populate it with all of the inputs. Again, this is all in documentation. The only important thing to see here is that under the data type, you can issue a list object, and what I've done is issued basically both kinds of rasters and vectors, both layers and data sets. So you can use this tool against content that just sits on disk, like a TIFF file or a shape file, or you can use it as actual feature classes, such as like that sit in a geodatabase, or layers that are actually loaded in your map viewer. Then you have an is licensed, and if you're designing your own tools, that's always going to be true. Update parameters. This lets you do some update parameters and update messages. Lets you do some pretty nifty script or geoprocessing tool validation before you actually kick your tool off and start running it. And maybe I'll do another video showing you some more in-depth stuff on how to write good tool validation. So the first custom method I've added in here is called makeTemp UTM FC, or feature class. And what this does is it basically just takes the GeoJSON string, and along with a spatial reference of 4326, which is pretty much what all GeoJSON is in, it will create a temporary feature class in memory of that UTM grid. So there's nothing being written to disk for most of this process, so it's very, very fast. You'll notice that as we run it at the end of this. And then we're going to add to that temporary feature class, we're going to add a field called EPSG. So in this UTM grid dictionary, you can see here we've already got EPSG codes added all the way down. So we can basically not just know what's my zone, but also what's the actual EPSG, or the factory code, for to do a more abbreviated form of the projection a little bit later. So basically we just create this. We use ArcPy's as shape method to read through the geometry of the GeoJSON data, and then we insert the rows into that temporary feature class and return it. So now we've got this kind of temporary GeoJSON derived UTM grid feature class that just sits in memory, that we can access like a normal feature class, but it's just much faster. The second custom method is just a simple helper method called getExtentCentroid. And so what we're doing with this is whatever data we're actually putting that we want to convert, we're going to figure out what its extent is, and then we're going to find out the center of that extent. And then we're going to use the center of that extent and intersect it with the GeoJSON grid. And a point can only intersect a polygon or a grid in one of the grid cells. So if you had, say, like an image that maybe straddled a seam line for those UTM cells, which is very rare, by the way, but if you had that kind of case, then at least if that 51% of the image was in one grid cell as opposed to the other, it'll take the one where more of the image is in, because the centroid would end up falling in that other cell. The theory for working with vector data is basically the same thing. You just take the extent, although you could also use something like a convex hull, which would basically draw the smallest possible polygon you can around your point data, and then find the centroid for that. But that also requires an ArcGIS advanced license, and so I'm just kind of keeping this for something that someone with a standard license could run. So we just basically use the extent and get the centroid from that. So Arc has some really super simple ways of extracting that information from a layer. So they've got sort of an all-purpose method called describe. Describe is just a method that just says, tell me what you know about this layer, this data set, whatever. So we're going to describe the input layer, and one of the properties of that describe object, if you're dealing with pretty much almost any spatial content, is going to be extent. Extent is its own class, and it has a a method called polygon. And so you can basically return the extent object as a polygon, but again, polygon has its own set of methods and properties, and you can string along this project as method. And again, I might be going fast, but all of this is in the documentation, and so you can pretty much see the hierarchy of and how it works. You go from the describe object to get the extent. The extent you can express as a polygon. The polygon you can project as, and what we're going to do is we're going to project that polygon in 4326. The reason we're going to do that is that even if we're not dealing with data that's already in a global coordinate system, maybe it's in some other coordinate system, the point is we want it in the same spatial reference as the UTM grid, which itself is in 4326. So and we do this so that the two will basically match up, and 4326 honestly gets us close enough. And the polygon also has a centroid property, which will now be returned in 4326. So we basically go from a layer to its centroid in WGS 84 4326 notation in really 2 lines of code. It's very, very straightforward and simple. And then the last required method call inside of a ArcPy Toolbox is the execute. And the execute, this is what actually gets kicked off when you when the user clicks run, when they run the tool. So what we're going to do here, we're going to express some environment. We're going to set our environments. We're going to get our current project in this line, and then we're going to basically say what we're the map we're working with is this project's active map. That's a property of the actual current project object. And then we're going to set our environment overwrite output flag to true, and that just means if I need to run the same thing over and over again, it's not going to give me a hiccup and say, oh, there's already a file named this. It'll just overwrite it. And then we're going to do the work right here. We set our global coordinate system first, 4326, and then we're going to access the layer that the user wants to issue you by looking at the parameters variable. Parameters, as it's issued to, this is a fixed name. You can't use another name for that. Parameters is again, it's a fixed name, and it returns as a list object, and then you access it by its index, and then it has properties. So in this case, we're accessing the actual feature class or raster layer or raster data set itself using the value as text property. We report some things to the user. We're going to say, hey, we're initializing the UTM grid, although it will probably be too fast for them to even see it. And we basically set the UTM FC variable with that helper method that we looked at above, that basically takes that UTM grid that's expressed in GeoJSON and it just pipes it out to a feature class in memory. Then we do basically we get the describe object for the layer in, because we want a couple of those things associated with that layer, like the name, like the location, the path. We're going to deal with that stuff later. And then we're going to get the center by piping that layer in that the user has given into the helper get extent centroid method. Now we're going to take that centroid and we're going to do the same thing with it that we did with the GeoJSON string, and that is we're going to create a feature class just for that point in memory, and that is because when you're doing a spatial join, it requires a feature class object. I can't just take a I just can't take a point geometry and use it as to spatially join anything. So this is all basically just creating that that centroid feature class right here. Now we run the spatial join. Once that's done, and the actual sauce of this is right here. The spatial join result object is an output of the ArcPy.analysis spatial join method. And we basically just say give it the centroid layer, the UTM layer, and we're going to put that result object also in memory. And I probably should have gone over that before, but if you're dealing with memory objects inside of an ArcPy script, you just use the word memory in a string like that, and it'll figure it out. Now we basically go get the the UTM EPSG code as a result of the spatial join. So we're only going to keep the one. We're going to keep the one grid cell that actually contains the EPSG code that we care about, and we're going to return that. Once we've got that code, then everything is super simple. Then it's just a matter of running a straightforward project if it's a vector data set, or project raster if it's a raster data set. And so all the rest of this script really is just basically figuring out, do I have a vector data set? Do I have a raster data set? What's the name of the input data? And where should I put the output once I've projected this content? You'll see a lot of replace. This is just because a lot of files can get shipped with certain content in their file names that can't actually be read by or are illegal characters rather inside of a file geodatabase. And so we basically replace those so that those are converted to legal characters. So we basically create a file geodatabase friendly name, and then we're going to tell it we're going to put it in the project geodatabase. And then at the end, once we've actually projected that data, we're going to add it to the map and then give the out layer or the output name, or the layer that got added to the map. We're just going to change the name to whatever the original name was with an underscore and then UTM. And that's basically it. And so I'll show you how it works. So here is just a JP2 unprojected file. Well, it's in 3857, so it's in Web Mercator. So if we look at the properties and go down to spatial reference, we see it is in Mercator auxiliary sphere. And so we want to convert this to UTM. We've also got, I just made a fake point layer of points, just called Charlotte points, and these are in also, well, these are in 4326. So basically two global coordinate systems. And so I've added my folder to my project. You can just add a folder connection, and I've put my script tool in this folder called UTM thing. Oh, one thing I should actually point out very quickly is that when you actually name your script tool, you want to give it a .pyt extension. And you can make VS Code read those as Python files. I can maybe mention that in another video or something. So anyway, here's our two unprojected data sets. First, we'll go ahead and project the point data, and we will open up our Python tool, and we see the label that we added in the script itself. It's called project as UTM. We're going to double click it, and it gives us an input field. Now we're going to just select whichever one we want. It's going to show both raster and vector content, or you can also browse to some content you want to convert. So we'll hit Charlotte points, and we'll just hit run. Done. So now you have a point layer, and if we check the properties and the spatial reference, we see that it has landed in WGS 84, but UTM zone 17 north. And so we should expect that the raster ought to do the same thing. So if we switch our input data set to the raster data, hit run, it caught the same EPSG code. And images can take a little bit longer. And it's all done. So now if we look at the properties of the output raster, which is now _UTM, we see that it is also now in 17 north. And we didn't have to go and load a grid and figure out which zone it ought to fall in. You can just run it, and it puts all of your geographic coordinate system stuff into linear unit, in this case meters. All right, if you got any comments or questions, just leave them below. Thanks a lot. Bye.